Welcome back to The Explainer. Today, we're unpacking a massive, literally tectonic shift in the world of computing. For decades, Moore's Law has been the golden rule that built our modern world. But the geometric era, that relentless, constant shrinking of chips, is effectively coming to an end. It's a huge turning point, and the way we engineer the future of tech is about to completely change.
So, we have to ask, what actually happens when the transistor just can't shrink anymore? For over half a century, the semiconductor industry basically had one main directive, right? Make the transistor physically smaller. But today, shrinking that physical space is hitting a huge economic and physical wall. So, what does the industry do now, that it can't just keep zooming in?
Okay, let's dive into this. $1 billion. Yeah, a billion. That is now the estimated design budget for a single 2-nanometer chip. Just think about that for a second. At the absolute bleeding edge of technology, the cost per transistor isn't falling like it used to. It's actually going up. And this perfectly frames the crisis we're exploring today. Relying purely on shrinking chips is becoming unsustainably expensive.
Here is our roadmap for The Explainer today. We'll start with the end of Moore's Law, then look at why time is the new space, followed by a mobile proof point with folding chips. After that, we'll see how this scales up to AI data centers, and finally, we'll look at the fusion of logic and memory. We're zooming all the way out from the microphysics of your smartphone to the macro architecture of the cloud.
All right, Section 1, the end of Moore's Law and the plateau of the geometric era.
For 60 years, semiconductor progress was measured almost entirely in nanometers. Smaller meant better, faster, and cheaper. It was an industry-wide compact. But this geometric era is plateauing, and there are a few real culprits here. Beyond the 7-nanometer mark, the returns from shrinking have seriously flattened out. First, we're dealing with velocity saturation, which basically means smaller doesn't automatically equal a faster intrinsic delay anymore. Second, there's rising parasitic resistance in the local interconnects. Those are the microscopic wires connecting the transistors, and they're turning into tiny traffic jams. And third, well, like we just saw with that billion-dollar figure, soaring mass costs and the massive depreciation of EUV machinery. It is simply getting way too hard and way too expensive to just shrink things.
Moving on to Section 2. Time is the new space. Let's look at this new optimization target.
This brings us to the core aha moment of the research we're breaking down today. Spatial scaling, making things physically smaller, was never actually the ultimate goal. It was just a tool. Think of it like your daily commute to work. Shrinking the transistor was basically just a way to shorten the physical distance of a signal's commute. But the actual goal? Reducing the commute time. Moore's Law, when you really get down to it, was never fundamentally about space. It was always about compressing time. Picoseconds at the device level, nanoseconds at the chip level, seconds at the system level.
So the crucial point is this entirely new concept, tau scaling. This is the proposed successor to Moore's Law. It adopts a single characteristic time constant, represented by the Greek letter tau, as the unifying optimization target across the entire computing stack. So instead of obsessing over nanometers, engineers are now obsessing over time. And this is not just some academic theory either. This is a massive paradigm shift that's already been tested on 381 production chips.
When we place these two eras side by side, the shift is super clear. Geometric scaling optimizes by shrinking physical dimensions, which, as we've established, is hitting a really expensive wall. Time scaling systematically reduces that time constant tau across 12 orders of magnitude. And what's so incredibly powerful here is that tau gives the process technologist who's building the physical silicon and the system architect designing the global network the exact same metric to measure success.
We can see this applied across the 4 different layers of tau scaling. You start at layer 1, the transistor, measured in picoseconds. Then layer 2, the circuit. Layer 3, the chip, and finally, layer 4, the system, which is measured in whole seconds. This is a complete zoom out from those microscopic switching circuits all the way to macroscopic global networks. Every single layer has its own tau, and improving the time efficiency of any of them improves the whole shebang.
Let's move to Section 3 and see how this builds into something tangible. We're looking at folding chips as a mobile proof point.
So how does this grand theory actually look in the real world, especially in the ultra-constrained milliwatt environment of a smartphone? Well, the answer is a breakthrough methodology called logic folding. Instead of placing logic gates on a flat, two-dimensional plane and routing wires over them, like a sprawling suburban city, logic folding partitions your digital, analog, and memory circuits across vertically stacked tiers.
It's literally like taking that sprawling suburb and building a dense, highly efficient skyscraper. It drastically reduces wire length and cuts down on that parasitic resistance we talked about earlier.
The results of doing this are absolutely incredible. By stacking vertically, engineers achieved a massive 55% reduction in the network-on-chip footprint and a 41% gain in power efficiency. And here is the absolute kicker. This was achieved at a fixed device node, meaning there was no need for a magical next-generation lithography machine to shrink the transistors further. They literally just reorganized the space in 3D to save time and energy.
Now, what's really interesting about this slide is the dramatic leap in performance right in the middle. Look at the transition from planar, or flat chips, to logic folding with the Kirin 2026. The CPU performance core frequency jumps cleanly to 3.1 GHz. And as logic folding evolves to multi-layer designs in the coming years, you can see a mapped-out, very clear path to 4 GHz and beyond by 2029. This is future performance unlocked entirely without relying on traditional geometric shrinking.
Okay, Section 4, Scaling Up AI Data Centers.
So what happens when we take a time-scaling theory successfully tested on a tiny phone and scale it up to a massive gigawatt data center? Because at the AI scale, data movement consumes over 80% of the energy. To kill latency here, tau scaling is applied across 3 coordinated layers. First, a unified bus, which is a memory-semantic peer-to-peer fabric. Second, high WAN, bringing high-density optical connections right near the package at a staggering 8 terabits per second. And third, 3D folding. Together, these drop remote access latency down to just 100 nanoseconds, essentially making a multi-rack AI cluster behave as one single system as one chip.
Now, to understand why reorganizing the package is so vital for AI, we have to look at a pretty fascinating geometry problem, the n squared versus n dilemma. See, in a traditional 2.5D chip, your compute capacity scales quadratically, as n squared. That means the processing power expands rapidly across the area of the chip. But your memory and I/O connections, they're stuck on the perimeter. They only scale linearly, as n, along the die's edge. So you inherently hit a massive bottleneck, where the super powerful center of the chip is literally starving for data, just because the limited edges can't feed it fast enough.
And this brilliantly illustrates the solution, 3D folding. By relocating power delivery, optical I/O, and high-speed memory off of that physical perimeter edge and moving it onto the vertical surfaces of the stack, you suddenly match the n-squared pace of the compute. Everything scales together quadratically. That geometric bottleneck, completely broken.
Which brings us to our final section, Section 5, Fusing Logic and Memory.
You know, back in the 1980s, during the old 8086 era, the industry deliberately decoupled processors and memory so they could scale independently. But in today's AI era, where moving data is the absolute biggest hurdle we face, that historic decoupling is rapidly reversing. Physically fusing logic and memory to shift to tau scaling is going to require solving some massive open challenges over the next decade. We're going to need entirely new 3D native tool chains to design these vertical chips. We have to figure out how to handle variations when bonding different silicon wafers together. We need to carefully manage the energy overhead of those vertical interconnects. And crucially, we have to establish completely new benchmarks that focus on continuous time profiles, rather than just static 2D metrics.
As the author of this paper, Ting-Bo He states perfectly, the era of acceleration through miniaturization is giving way to an era of acceleration through tau optimization across the multi-layered electronic system. This marks a fundamental shift in the industry. The strategic weight and the investment are actively moving away from pure lithography equipment and heavily toward advanced packaging, 3D stacking, and fabric design.
Which leaves us with one final, pretty provocative question. Is the industry actually ready to abandon the geometric era and fundamentally fuse logic with memory to conquer the next decade of computing? The roadmap is definitely there, but it's going to require a massive collaborative shift. Thank you so much for joining this explainer. Keep rethinking the future of hardware, and we'll see you next time.